Hello, welcome to this lecture of hyperbolic geometry. In the last lecture, we have learned about the disk model of hyperbolic plane. So using that model, here we'll be doing hyperbolic trigonometry. So we'll be proving a sine rule and two cosine rules. So this sine rule and the first cosine rule, so they are just analogs of sine rule and cosine rule, so that you have seen in Euclidean geometry. And using this sine and cosine rules, we'll be also proving the Pythagoras theorem in hyperbolic plane. So let us begin. So let me first write down the sine rules and the cosine rules. So the first one is my sine rule. So you take this geodesic triangle in your this unit disk with hyperbolic metric. So this is my triangle. So with vertex angles alpha, beta, gamma, and the sides, length of the sides are given by this A, B, C. So what is the sine rule? It is sine hyperbolic A by sine alpha is equal to sine hyperbolic B by sine beta, and it is equal to sine hyperbolic C by sine gamma. So this is the sine rule. And what is the first cosine rule? So cosine rule 1. So cos hyperbolic C is equal to your cos hyperbolic A times cos hyperbolic B minus sine hyperbolic A times sine hyperbolic B times cos of gamma. And the third thing is the cosine rule 2. So cos hyperbolic C is equal to your cos alpha cos beta plus cos gamma whole divided by sine alpha sine beta. Okay, so let me tell you this thing. So what is the significance of this cosine rule 2? So suppose if I take two triangles, so if delta prime are two geodesic triangles, in this hyperbolic plane, so here either you can take disk model or upper half plane model. So both are isometric to each other. So all these sine rules, sine rule and cosine rules, so they hold in both the models. So if this delta and delta prime are two triangles with angles of delta and delta prime are same, then so this delta is isometric to delta prime. So this is an application of this cosine rule 2, because when this alpha, beta, gamma, so they are same, so cos hyperbolic C will be equal to cos hyperbolic C prime. So from there, so the C is equal to C prime. So therefore, the length of the sides also they will be equal. So therefore, so those two triangles will be isometric to each other. So this thing, it doesn't happen in your Euclidean plane. So in Euclidean plane, you can have two triangles with same angle, vertex angles are same, but their side lengths are different. So that you can always have. Okay. So let me write down another corollary of this cosine rule 2. So this is my Pythagoras theorem. So you take a triangle. So this is my geodesic triangle, either in upward half plane or in the unit disk. And so one vertex angle is your this 90-degree. And these are my sides. ABC are my sides. So by this cosine rule 1, so what I have, so cos hyperbolic C is equal to cos hyperbolic A times cos hyperbolic B minus sine hyperbolic A times sine hyperbolic B and cos of 90 degree. So cos of 90 degree is 0. So therefore, so cos of hyperbolic C is equal to cos hyperbolic A times cos hyperbolic B. So this is the Pythagoras theorem. So this is Pythagoras theorem. Okay. So now let me come to the proof of this theorem. So I'll be first proving this cosine rule 1. From that, this sine rule will follow. And for these two things, this cosine rule 2, again it will follow. So first I'll give a proof of this cosine rule 1. Okay. So we'll work with the disk model of hyperbolic plane. Yeah. So you start with a unit disk. So z is a complex number such that mod of z is less than 1. And what is the hyperbolic metric here? So d squared is equal to your 4 mod dz square whole divided by 1 minus mod z square and the square of this thing. Okay. So now let us take this. So this is my unit disk. This is my origin. So let us first take this geodesic. So this origin, and let us take this point to be REI theta. So first, so what is the length of the segment? So this geodesic segment. So length of geodesic segment yeah, so let us represent in this way. So this geodesic segment, this is that geodesic segment, the length of which we are computing. So with respect to hyperbolic metric, what is the length of this thing? So here note that so r is varying and theta is your constant. So r is varying and theta is constant. So z is equal to REI theta. So dz is equal to your dr EI theta plus I EI theta d theta. So d theta is equal to 0 because theta is constant. So this will be equal to dr times EI theta. So as theta is constant. So therefore what we have, mod of dz is equal to your mod of dr ei theta. Mod of ei theta is equal to 1. So we have this thing here. So mod of dz is equal to mod dr. So therefore, so length of this segment is basically equal to, so this integral 0 to r mod of dz. So you are taking the square root of, so you are taking the square root of this thing. So in the numerator, so you will have this thing. So twice dr divided by 1 minus r squared. So if you want, I can replace this by capital R. So you have this thing here. So this is exactly equal to your log 1 plus capital R by 1 minus capital R. And again, we know that, so this is a geodesic segment. So this is a geodesic. So therefore, distance in this unit disk of 0 to r ei theta is equal to your log 1 plus r by 1 minus this capital R. So you have this thing here. Okay, so if I call this to be my t, so this capital R, so this is equal to, one can show that this is equal to your tan hyperbolic t by 2. So you can in fact do this exercise. So if I take any 2 points in this unit disk, so tan hyperbolic half of this distance between z and w, so this will be equal to your mod of z minus w divided by 1 minus zw bar. And the second one is sine hyperbolic square of half of the hyperbolic distance between zw is equal to mod of z minus w divided by 1 minus mod z square times 1 minus mod w square. So suppose you have done this exercise, and now we are ready to prove this cosine rule 1. Okay, so let us take a triangle. So let ABC be a triangle in your unit disk. Suppose this is my triangle. So now what we can do, with the help of an isometry, I can take this triangle whose one vertex lie at origin and one side of this triangle, it lies on this real axis. Yeah, so we can always do this thing. So I have an isometry which take this triangle to your OAB. So let me write down this thing. So there exists an isometry of this unit disk such that, so let me replace the name of this triangle to be or by PQR, such that f of P is your this origin, f of Q is your A, and f of this PQ, so this is my OA. So PQ is the geodesic joining this P and Q. OA means the geodesic joining this origin at A, and f of R is equal to your this B. Okay. So because this f, it is an isometry, so if I prove the cosine rule for this OAB triangle, so then we'll prove the cosine rule for this PQR triangle as well. Okay, so now we have this triangle OAB, and this angle is given by your gamma. A and B are my complex numbers. So this OB, so in fact it will be, because this OB, it is a geodesic, so it will be a straight line. So this angle is your gamma. So AOB angle is your gamma. So this B, it is a complex number. It lie in this unit test. So this B is nothing but mod of OB times EI gamma. Okay. And now, so observe that. So tan hyperbolic half of distance between O and A. So this is equal to your this mod of OA. So this follows from here. So tan hyperbolic d by 2. So d is the hyperbolic distance between this 0 and REI theta is equal to R. So R is this mod of this REI theta. So therefore we have this thing. And A lie in the on the real axis. So, and again we are assuming that this OA, it lie in the this so again we can assume this thing. So this real part of this A is greater than 0. So therefore this mod of OA is nothing but is equal to your A. So yeah, A is a real number which is positive. Okay. And by the representation of the lengths, so this is my triangle. So we have taken the lengths to be your this ABC. So according to this picture, so what do we have here? So hyperbolic distance between A and B is C. So this angle is your gamma. This length, uh, this opposite to vertex B is, this length is B, and this length, distance from O to B, so this is is equal to A. So therefore what we have, so tan hyperbolic of B, so this is equal to your A. And similarly, so tan hyperbolic half of A is equal to your this mod of OB. So again, so this B is mod of OB times EI gamma. And this mod of this OB, so this is again tan hyperbolic half A times EI gamma. So we have this thing here. So, and also, so the C is, so this C, so this is nothing but the hyperbolic distance between these two vertices, A and B. And by this formula, so you have to use this formula, use this thing. So we know that this cos hyperbolic C is equal to your twice sine hyperbolic square by 2 plus 1. So this thing we know, and this is equal to twice sine hyperbolic square. C is just the hyperbolic distance between A and B. So this divided by 2 plus 1. Yeah, so one mistake I have made. So this will be sine hyperbolic square C by 2. Yeah, twice 2 sine hyperbolic square C by 2 plus 1. So you have this thing here. So now you use this 2. So from here, so what we'll get, so from 2, so cos hyperbolic C is equal to your uh, twice mod of A minus B whole square divided by 1 minus mod square times 1 minus mod B square plus 1. So you have to use this thing, this exercise 2, to get this thing. And now, so cos hyperbolic C is equal to your twice. So we know A and B. So this is A is tan hyperbolic B by 2 minus B is a complex number. So that is EI gamma times tan hyperbolic A by 2, take the square, divided by 1 minus tan hyperbolic B by 2 square of this thing times 1 minus, so mod of A, we know that it is equal to tan hyperbolic B by 2. So that's why we have this thing. And now 1 minus square of this tan hyperbolic A by 2 plus 1. So we have this thing here. Now if I use the formula for this tan hyperbolic, so you can prove this thing. So cos hyperbolic C is equal to your cos hyperbolic A times cos hyperbolic B minus sine hyperbolic A times sine hyperbolic B times cos of gamma. So therefore we got this cosine rule. So this is my cosine rule 1. And what about the sine rule? So again, it is just a manipulation. So you just compute this thing. So sine hyperbolic C by sine gamma whole square. So this will be sine hyperbolic square by, so 1, yeah, so sine square gamma is 1 minus cos square gamma. So from this cosine rule 1, so what we have, so this is 1 minus cos hyperbolic A times cos hyperbolic B minus cos hyperbolic C whole divided by sine hyperbolic A times sine hyperbolic B square of this thing. So now I'll jump some step, and finally, so what we'll get, sine hyperbolic square A times sine hyperbolic square B times sine hyperbolic square C divided by 1 minus sum of this cos hyperbolic square A plus cos hyperbolic square B plus cos hyperbolic square C plus twice cos hyperbolic A times cos hyperbolic B times cos hyperbolic C. So this right hand side, so this is symmetric in your ABC. So if you replace by A by B, B by C, C by A, so you'll get the same formula. So therefore, so one will have this thing. So this will be exactly equal to sine hyperbolic B by sine beta whole square. And this will be again equal to your sine hyperbolic a by sine alpha whole square. So this will imply that this thing, sine hyperbolic a by sine alpha is equal to your sine hyperbolic b by sine beta is equal to your sine hyperbolic c by sine gamma. So this is my sine rule, and I'll leave this cosine rule 2 as an exercise. So prove cosine rule 2. So this will follow from this cosine rule 1 and sine rule. Okay, so I'll stop here.